Good afternoon, and thank you for joining us today for a special webinar on sealing systems energy efficiency, sponsored by AES Seal. I'm Lori Siegfried from the Hydraulic Institute's Educational Services. Today's presentation will last approximately 45 minutes, with an additional 15 minutes allowing for Q&A. Please note that in the lower right-hand corner of your WebEx window, there is an area for typing questions. You can submit them at any time during the presentation, and we'll address them at appropriate periods during the webinar. This presentation is brought to you by AES Seal, a global manufacturer of comprehensive sealing packages covering everything from shaft packing and flow meters to seals and systems. In addition to sponsoring this webinar with AES Seal, the Hydraulic Institute and Pump Systems Matter provide other tools and education to the pump user industry with emphasis on energy efficiency and bottom line savings. This webinar is the first joint and exclusive event between the two organizations. The Hydraulic Institute is internally known for leading the pump industry with standards and guidelines. Be sure to visit www.pumps.org for information on our available resources and how you can have a positive impact on the future of the pump industry. To learn more about sealing systems, visit www.aesseal.com. I'd like to introduce you to our subject matter expert presenter, Richard Smith. He served as the Director of Oil, Gas, Petrochem Development at AES Seal since 1990. Richard's at the forefront of business development initiatives for AES Seal in the oil and gas and petrochemical markets, responsible for the development of products for both upstream and downstream applications. Prior to joining AES Seal, he trained as a design engineer with the Ford Motor Company, specializing in both production and product development. Richard also possesses broad-based knowledge of the power generation, pulp and paper, chemical process, mining, and food industries. In addition to being a member of the API 682 Task Force for the 4th edition, Richard has published a number of papers published by the IMEC-E, Texas A&M Pump Symposium in the British Hydraulic Research Group. So at this point, I'm going to pass you over to our presenter, Richard Smith, and I hope everybody enjoys it.
Good afternoon to everyone. I'm presuming most people are in the afternoon, although I'm sure we span a few time zones and some people are in the morning. So good morning to you as well. My presentation today is about energy efficiency, in particular in sealing systems for pumping equipment. And the subject of energy, the topic of energy, has been become more and more of a interest group throughout the world. Now, in Europe and in my country, which is the United Kingdom, there was a survey done, and there was an estimation that 10% of electrical power that is used in my country is used for pumping equipment, for pumping fluids. And I'm guessing that is the same across the world, in the North American continent and across the developed world. The regulatory bodies of our countries who are focused on energy efficiency and energy conservation are all beginning to look at pumping equipment and pumping systems and energy efficiency. In Europe, we've already legislated for small circulating pumps for domestic water heating in houses and such like. And pumps now that are placed on the market within Europe have to meet a certain efficiency threshold to be allowed to be sold. The US Department of the Environment is also beginning this process, and there is a consultation document or a framework document that is being developed and is in consultation. And it is likely that legislation will affect the North American continent in the next few years. If you want more information on what's going on with the Department of Environment, there is a bulk of material available on the Hydraulic Institute website with the website address as shown on this slide. Additionally to lawmakers and regulatory bodies, international standards writing bodies are also similarly focused on energy efficiency. The ISO International Standards Organization, based in Geneva in Switzerland, is developing a standard. It will be called ISO 14414, and it's the standardized way of pump system energy assessment. This standard is in its final international draft, currently circulated around all the member countries of ISO. And it is anticipated, I was speaking to the convener of this standard, and he was anticipating publication at the end of this year. So a lot of this focus is on electrical power and conservation of electrical power. But energy isn't just electricity. So where does electricity come from? It comes from a power plant. And in a power plant, most conventional power plants are fired by fuels such as coal or gas or oil, and we burn this fuel to create heat, and in the majority of instances to create steam, to turn turbines and create electricity. So energy is it can be in the form of heat or thermal. And if we look at a typical power plant producing electricity, it uses water in a closed-loop system. The water is at various energy states around that system. So the water could have a high energy state being feed water or steam, or a slightly lower energy state being a condensate. And any of this water in this closed-loop system that has to be replenished has to be heated up. So if we're leaking of this water with the high energy content through valves or valve stems or steam traps or pump seals or flanges, this will have to be made up in what's known as make-up water. Now typically the make-up water would be at a low energy state, a low temperature. And there was a calculation done by a friend of mine who's in the Fluid Sealing Association, and he made the assumption that if 50 gallons per minute of water is lost throughout that closed-loop circuit, to make up that water and heat it up to the same energy state, the equivalent energy requirement would be that of 3,200 homes in North America. So thermal energy has a significant impact on plant efficiency. Another example that I'm going to state here is an evaporation process. Now you find evaporation processes in many industries. In the paper industry you find that lignin is an extract from the wood or the lumber and is turned into a liquor called black liquor. The black liquor is evaporated to drive off all the moisture content and is then used to fire the boilers, which in turn create the heat for the paper making process. Now this black liquor is pumped around, and I'm just going to give a very clear example here of where the problems start arising. So I've got an evaporator here where I'm trying to drive off the moisture. I'm applying heat. I'm probably pulling vacuum in the evaporator. And I've got a pump that's pumping liquid, either circulating it or feeding the evaporator. And I've got a seal in here. And if I'm injecting cold, clean water into this evaporator, I'm actually trying to cool down the evaporator. And the volume of cold liquid going into that evaporator through the seal flush point here can have a significant impact on evaporator efficiency. And we'll look at that further on in this presentation in a little bit more detail. So we can make decisions and we can implement things to optimize energy efficiency and improve reliability by having a greater knowledge and improved understanding of the impact of these seal flushes that we use. And I think the concept that we need to start coming across in the seal industry, we always talk about sealing the process fluid, be it toxic or be it expensive. We try to keep it within the system, within the pipework, and stop it leaking out to avoid the cost of waste. But if that liquid is leaking, we're actually, and the liquid is heated, we're actually sealing the heat energy of the process too. So be it through flanges, valve stems, or pump seals, we must start thinking in the concept that seal containment is the process, but we're also containing energy within the system. There's quite a lot of discussion on shaft sealing and the different methodologies of shaft sealing and what impact that has on the driven power of a pump, and certainly coupled pumps using some sealing mechanism are more efficient than sealless pumps that have losses through the coupling, the magnetic coupling. There's a lot of discussion in the industry about optimization of pump hydraulics and variable speed drives and other improvements. However, the thermal inefficiencies of some sealing systems and some sealing flush plans can far exceed the energy savings by hydraulic optimization. We also look at the frictional absorption of seals or different sealing devices, and this chart shows different sealing devices by shaft diameter and the energy absorption. But the energy absorption, if you're looking at relatively small seals, 2-inch diameter, is quite low, and we're talking of a few hundred watts or sometimes maybe more than a kilowatt, but we're talking maybe 1 or 2 horsepower as a maximum power absorbed by the sealing mechanism. And in this grand scheme of things, relatively low in terms of when we compare it with thermal efficiencies of sealing systems. I've just put this slide up here to, it always makes me laugh, this slide. We've got this was a petrochemical facility that I saw. It was in southern Africa. It's one of the largest facilities in the continent of Africa. And if you walk around the plant, you see steam leaks from valves, you see steam traps leaking continuously, you've got large cooling towers, and all this thermal efficiency. And this was on a beautiful sunny day, and as you can see above the petrochemical facility, there's a cloud formation. And this cloud is being formed by all the thermal inefficiency within that process plant. But when you walk around the offices, you are bombarded with posters asking all the employees to save energy. And they're talking about turning off their laptops at night or turning off their phone chargers at night. And it really, in the grand scheme of things, the futility of turning off those small apparatus is nothing in comparison to the thermal efficiencies that you find in process plants around the world. The focus area I'm talking about is on the thermal inefficiency of a seal flush or a seal piping plan or a seal auxiliary system, or whatever we want to call it. The frictional power consumption of a seal is relatively low in comparison. And I'm going to make an analogy here with, that's a European car, it's a French vehicle, and in Europe it was the first vehicle that was meant to be exceeding 1,000 horsepower and could travel at over 200 miles per hour, a road legal vehicle. And if you have a few $1 million, you can go out and buy one of these things. Now, when they say the manufacturers claimed it was a 1,000 horsepower, of course they were talking about metric horsepower, which is not the same as brake horsepower, but of course it's French, so we have to work in metric. And the other claim that a 1,000 horsepower vehicle is not quite correct. Now, the actual engine within that vehicle produced over 4,000 horsepower. But what we look at is actually the horsepower that turns the rear wheels, that spins a shaft, the prop shaft that turns the rear wheels. That is a mere 1,000 horsepower. The other 3,000 horsepower was wasted energy exiting through the muffler, up the exhaust system, and through it's had something like 10 radiators hanging around this car to cool the engines, to cool the gearboxes, etc., etc. So 3/4 of the power produced by this vehicle is wasted thermal energy, and only 1/4 of the power is actually used to drive the vehicle down the road. So we use, when we have sealing devices in pumping equipment, we use things which we call flush plans or auxiliary sealing systems, or some people might know them as API plans. Why do we use them? Again, I'm going to use another analogy. In my country, in the United Kingdom, we have quite a cold climate. We're at a high latitude. We're at 51 degrees north. And here's a picture of a glass house in London where we grow tropical plants. And we can grow them in our harsh climate because we change the environment that they live in, and we keep them in this enclosure, which allows them to flourish. Now, mechanical seals and sealing systems, seals on pumps, are probably the most delicate component on a pump, and they're, again, like delicate little tropical flowers, and we use seal flush plans or API piping plans or sealing systems to change the environment that our seals are working in, are operating in, and that makes the seals flourish and provide reliable longevity in operation. So flush plans are normally to change the environment of a seal. Now, the flush plans are formalized in the American Petroleum Institute in their standard API 682. It's the custodian of the flush plans, and they're drawn in there as standardized formats. If you want to learn more about these flush plans, how they're used, how they're operated, there's an excellent tutorial in a Hydraulics Institute publication, Mechanical Seals for Pumps Application Guidelines. It's in Chapter 20, and a very recommended read for anyone who wants to learn more. So sealing systems contain energy as well as fluids. Some sealing systems will use more energy than the pump driver. Market research carried out by the Fluid Sealing Association has illustrated that inefficient sealing systems are regularly used. Where are these inefficiencies? Where do they come in from? Where do we find them? Well, if you look at recirculation lines in seal flushes, they can reduce the efficiency of a pump. External cooling can reduce the thermal efficiency of a process. External injection that may have to be later removed by processes such as evaporation can be extremely expensive. Externally injected flush fluids may contaminate the process fluid and have to be separated further downstream and then treated before disposal. External circulating systems for dual seals will require some sort of mechanism to circulate them, maybe pumps. These are all potential inefficiencies that we see with flush plans. The plans are numbered, as I said earlier, formalized, and the numbering system, don't ask me how to explain the numbering system. It doesn't seem to really follow any logic. But then flush plans Here I'm showing this was a survey carried out by the Fluid Sealing Association for pumps of 28,000 seals, and where they were sealing process temperatures exceeding 200 degrees C or 400 F. The study showed that these were the most popular flush plans used, and then by comparison, this second graphical image here illustrates the energy absorption potential from each of the flush plan. And interesting to note, flush plan 32, which is the second most popular flush plan in this survey, is by far the highest energy user of all the flush plans. So, can we summarize between the API plans which ones are used for single seals, which ones are used for dual seals? These are the questions that if you want to have an impact, you have to have an understanding of the piping plans. What do the plans really do? How do they control the environment? Again, knowledge is power here, and reading and understanding the flush plans is critical if you want to make an impact on thermal efficiency or energy efficiency in seal systems. How many plan options are there? Which ones do we choose? Are there new plans? Have they been adopted? Well, currently API 682 is in its 3rd edition, and there are some 28 current plans. The 4th edition of the standard is imminent, due for publication, and there's an additional 5 plans in the new edition of API 682. So there's over 30 plans to choose from. We're going to look at some studies of different piping plans. These studies were undertaken by members of the Fluid Sealing Association, and we're going to compare them with a hypothetical case study. The piping plans that we're going to look at in a little bit of detail are Plan 21, Plan 23, Plan 32, Plan 62. We're also going to look at some dual seal piping plans, Plan 53A and Plan 54. So I'm just going to briefly try and describe some of these piping plans so people have a good understanding of them. So Plan 21 is very commonly used on high temperature process fluids. If we look at the cross section of the pump here, we take liquid through the impeller, from the suction side of the impeller through the discharge and up through the discharge pipe flange. And what piping plan 21 does, takes a simple side stream from the discharge, which is at higher pressure than the seal chamber, which is at the eye of the impeller. So the higher pressure drives this side stream of this hot liquid through an orifice plate that controls the flow, then through a cooler, and then the cooler liquid is injected on the seal flush over the seal faces, and then is lost back into the process. So it's a sort of open loop cooling system. By comparison, this is Plan 23, which is a closed loop cooling system. So again, we have our hot process going from suction to discharge on this pump. The seal chamber is closed down by some throat bushing at the neck of the seal chamber. And what the seal, or within the seal chamber, we have a secondary, very, very small impeller to circulate liquid locally through a cooler or a heat exchanger. And this Plan 23 is significantly more efficient than the Plan 21, because we're only really trying to remove the heat from the generated heat from the seal faces and any heat soak through the pump casing, as opposed to the Plan 21, where we're trying to cool down the process continuously. Plan 32 takes so we've got the hot process, or a process here where we're, again, suction to discharge, and in this plan we're injecting a clean, cold liquid from an external source through some controls here, but effectively it's a constant loss of cold, clean liquid into the process. Normally the cold, clean liquid would be significantly cooler than the process fluid, and we're effectively diluting the process with cold liquid, which can have a very significant impact on the thermal efficiency of the process. Plan 62 is an atmospheric plan commonly used on hot oil type applications for a single seal. And what we do with a Plan 62 is we take steam across the atmospheric side of the seal and down to some drains system. What the steam does is not really used for cooling. What it's used for is to carry away any hydrocarbon particles that congeal on the atmospheric side of the face. It carries them away before they start carbonizing and causing the seal faces and the seal to hang up. The case study I'm going to review is a hypothetical example developed by a member of the Fluid Sealing Association. He's looked at a simple example of a API 610 end suction pump, an OH2 pump. Pump fluid would be at 600 degrees F. We're talking about a heat transfer type oil to circulate heat around a plant, and we're assuming that the seal chamber is at 50 psi and the seal diameter is 2 inches. Typically a pump such as this would use a 40 horsepower motor, which is around 35 kilowatts. So we look at this example with a Plan 21. So as I said before, we're taking the side stream from the process through the cooler and injecting once through the cooler and injecting back to the process. Because we're cooling the process continuously, the heat load is very significant on the cooler. The only thing controlling the flow is the orifice plate, and if we do a simple orifice plate calculation across the pump, typically you see between 2 and 3 gallons per minute of flow rate through the cooler. The cooler works very hard, and in this particular example, the cooler is removing 37 kilowatts of heat, or 127,000 BTUs per hour of heat from the process, as opposed to the friction value of the seal, which is a few hundred watts. So a very significant load on the cooler. I'm just going to illustrate this schematic here because this really does illustrate what's going on. So we've got side stream going through a cooler, and I've got over 30 kilowatts of heat being sucked out the process and taken away to the cooling towers and to atmosphere. So a hot process here, we're trying to put heat in, and we're stripping out 37 kilowatts of heat and throwing it away to the atmosphere. And in this particular example, the heat load on the cooler, the seal cooler, is more energy than the pump driver, the electric motor driving the pump. The next example I'm going to look at is the Plan 32, where we're injecting a cold clean flush into the process fluid, into the stuffing box or the seal chamber, and a constant loss. So if we've got 300 degrees, 600 degrees F of process temperature here, and we're putting a cold, say for example kerosene in at 100 F, we're cooling down the process. So somewhere in the process we're applying heat to compensate for this cold liquid that we're injecting. I'm going to give an example here of what we're actually doing here. If you're sitting in your bath, your tin bath at home, and you've filled it up with hot water, this system here is like having the cold tap continuously running into your hot bath. And very quickly your bath loses temperature, and you're continually having to apply heat energy from your hot tap to constantly compensate for this constant loss, this trickle of cold liquid into your hot bath. The energy to heat up 2 gallons per minute of kerosene from 100 degrees F to the full process temperature would be in the region of 47 kilowatts or 160,000 BTU hours. So a very significant energy requirement indeed. Plan 23 is a more efficient piping plan. We've got a closed loop circuit here, and we're only dissipating the heat that's generated at the seal faces and the heat soak through the seal chamber casing here and the seal gland plate. The consequence of this is that the seal is operating, the cooler is operating at a significantly lower duty. We're talking probably in the region of 1.7 kilowatts of heat being dissipated through the cooler. And the result of this plan as well is that the seal itself, the seal chamber temperature, is significantly reduced over the plan 21, the first slide that I showed you in this sequence. If we look at the steam quench, which is potentially quite an energy efficient way of sealing a hot oil pump. So we've got our hot oil pump here with 600F. In a steam quench, we're not really removing much heat with the steam quench, so we have to use something like a bellows seal with graphite that will accept the full process temperature. The steam is there really just to remove or prevent coking on the outside, on the atmospheric side of the seal. Now, how much steam is required? A whisper of steam is all that is required to work on, to make this system work well. And a whisper of steam does not consume a lot of energy, less than a kilowatt. However, controlling the steam flow on a steam quench on a seal is not easily done, and is very commonly used in refinery service, this type of seal and system. And you often see pumps with the steam quench blasting outside the atmospheric side of the seal. So when steam is uncontrolled like this, the energy usage of the steam goes through the roof. Something like 1 pound of steam per hour is 0.3 kilowatts or 1,000 BTU. Very quickly, the steam quench system, if not properly controlled, will become very energy inefficient. There are methods of controlling the steam, but poor operating practice is typically a cause for concern on steam consumption on this type of piping plan. Out of interest, this plant I took this photograph in France. This was a refinery in France that had loads of operational issues. I surveyed the plant, was looking at the steam quenches, and found numerous pumps with steam, Plan 62 steam quench leakage, very high levels of leakage rate. The consequence of this was that the plant was actually shut because it was inefficient, and it closed. And I'm sure that all the bad operating practices, not just this, were contributors to the plant's poor profitability and sad closure. Another option would be to use a gas seal, a Plan 74, which generally uses a nitrogen flow to a dual seal, and the seals run on the nitrogen rather than the process fluid. There is some leakage of nitrogen to the process, and clearly the seal would have to be able to tolerate the full process temperature, as the gas itself does not really remove any heat. But this potentially is the lowest energy or the most energy efficient piping plan for sealing hot surfaces. One does have to consider the nitrogen leakage to the process, and one does also have to consider that there is an energy cost in producing nitrogen in the first place. Plan 74, here's an example of, or a better illustration of how it works, but fundamentally nitrogen gas is at a higher pressure than the seal chamber through some controls and flow meters and into the interspace between a dual seal, and the seals are running on nitrogen. The next item I'm going to look at is another case study. This is on water-based slurry type applications. Water-based slurries are common in pulp and paper, wet corn and milling processes, sugar processes, wastewater treatment, mining, mineral and power generation. The default option for these type applications is Plan 32, which is the clean water injection, and that seems to be very high instances of this piping plan used in this industry sector. I'm going to look at an evaporation plant. Now, you find evaporation plants, you find them in the ethanol industry, where the fermented mixture, the byproduct of the fermented mixture goes to an evaporator plant where the water is driven off and the solids are used as a cattle feed. Or you'd have a similar process in the paper industry with black liquor sealing, where we're trying to dry the water off and use the black liquor to fire the boilers. So quite a common application. And if we look at a pump, so here we've got an ANSI type pump, ANSI B73 compliant pump. The water slurry is at 75 degrees C. Again, we're talking about a 2-inch seal, 3600 RPM and 50 psi in the seal chamber. The schematic, as I showed before, so we've got a Plan 32 cold water injection directly into the seal chamber, cooling down the process fluid, and that cold water has to be driven off in the evaporation process downstream. The energy impact of that is very significant indeed. So if we've got 6 litres of flush fluid at 50 F, and we've got our process fluid being cooled down by this flush fluid, the heat energy that needs to be applied to warm that liquid back up to the process temperature and then evaporate it is in the region of 260 kilowatts. So a massive energy impact that this type piping plan or flush system has on a evaporator process. I did a survey in a plant in Scotland over a decade ago. Now in Scotland they don't make ethanol, they make a very similar product in evaporator plants, and it's called Scotch or whiskey, Scotch whiskey. Very similar to ethanol production, except the end product is significantly more expensive. I did a survey of some evaporator plants and concluded that the Plan 32 was having a dramatic impact on the evaporator process. Now, Scottish engineers are very, very good engineers. In fact, if any of you are old enough to remember the original series of Star Trek, the chief engineer on the Starship Enterprise was a Scotsman, Scotty. So they're very good engineers. But the other thing that Scotsmen are very, very renowned for is being very careful about spending money. And in this particular plant, the Scottish engineer was reluctant to spend money to change his flush system and to change his sealing device. So eventually we persuaded him to actually take a seal and seal system on loan for 6 months, and he would pay for it at the end of 6 months. Within 12 hours of the installation of that seal and sealing system, the engineer was on the phone saying that they had had a 10% increase in evaporator efficiency, and they wanted to convert all the other pumps within the evaporator plant. So a very, very significant impact that Plan 32 will have on evaporators. Alternates for this type of sealing, you could use a dual seal. Dual seals run on a barrier fluid that is a clean fluid. We're not now running on the process fluid, a pressurized barrier fluid. A Plan 54 is quite commonly used, and the barrier fluid is circulated by an external pumping device. The power consumption would be in the region of about 2 kilowatts. And a lot of this power consumption is the device that's used to circulate the barrier fluid. So if I go to the next slide, so here we can see a small little pumping device used to circulate the barrier fluid through a seal, back to the tank, and back through the seal. And quite an energy efficient way of doing it, but you have the complexity of some sort of circulating system. Another way to do it is to use a Plan 53, a very simple system, and instead of having an external pump, we put a little circulating pump within the seal itself that actually circulates the pump through a tank system, pressurized tank system, backwards and forwards to the seal. The heat load really on this seal is a little bit of heat soak, heat transfer through the casing of the pump, through the gland plate of the seal, and also the generated seal heat from the two seal faces. So typically this system would be around about 1 kilowatt of sealing power required. Here's a better schematic of a Plan 53A. There's all sorts of variations of Plan 53. API recognizes 53A, 53B and 53C, but there's other variations of this plan out on the marketplace that are very commonly used in the water-based or aqueous-based industries. Another way of doing a water slurry would be to use a dead-ended seal with no flush plan on the seal at all. The friction of the seal would be the only power that would be absorbed in this system. However, if you're pumping a hot sticky liquid such as liquor, black liquor, or a sugar syrup or something similar, the reliability of the seal would be compromised. What you're sealing between the seal faces is the process fluid. Those process fluids would tend to congeal on the atmospheric side of the seal, and that might have a negative impact on reliability. So in conclusion to this presentation, potentially sealing system savings can exceed the energy savings from switching to things like variable speed drives or improving pump hydraulics. Selection of inappropriate sealing systems can have very significant impact on the thermal efficiency of plant and plant utilities. Sealing systems found in many industrial applications are extremely wasteful of energy, and as I said before, the power output can exceed the power required to drive the pump. The sealing industry has got technologies that can overcome some of this energy wastage, and there's increasing publicity about some solutions. The Fluid Sealing Association has conducted a survey, and it illustrates some of the frequent energy wasting seal systems on the marketplace. The Fluid Sealing Association also has a return on investment calculator on its website that you can actually calculate some of the energy requirements within fluid sealing systems to assist in decision making. Being able to choose between different sealing systems or flush plans requires a very good understanding of the principles of their operation, why they are used, and also a good understanding of the process that surrounds the seals. So that concludes the presentation. There is a quarter of an hour here, I believe, left for anyone to ask questions if they have some. I've got a question that someone's written in that I'll attempt to answer. The question is about the steam quench, and is there any negative impact from a high level of steam or a high mass flow rate of steam other than the thermal inefficiency? To answer that question, probably not. If there's a high flow rate of steam to the atmospheric side of the seal, I can't really see there's a negative impact apart from the wasted heat. If it's an extremely high flow rate, you might find that the flow of the steam under the steam baffle might upset the balance of the bellows mechanism that's operating in there, just purely by the pure velocity of the steam passing under the bellows. Well, I can't really see any other negative impacts apart from the pure waste of heat going to atmosphere. There's a note here that I'm just reading that someone said, what is the power plant, the capacity of the power plant that I used in an earlier slide? The answer to that question is I don't know. That illustration came from a colleague of mine at Fluid Sealing Association, and he just used it as a typical, so whatever a typical capacity is in the USA, I don't know, but perhaps I can try and find out the answer to that after this session. There's a question about boiler feed pump using packing. Would there be an energy improvement in energy efficiency by using mechanical seals? Potentially, yes. If it depends what leakage rate there is from the packing. If there's a high leakage rate from the packing, then that is hot water that's going to drain. If the packing box is well maintained, I would suspect that the thermal energy loss would be relatively low. The only other energy absorber in the packing is the friction of the packing material. With packing, obviously, it is very, very dependent on how well the packing is maintained and the integrity of the shaft sleeve that the packing runs on. And I think probably the principal benefit of converting a boiler feed from packing to a mechanical seal would be a reliability advantage. That's just a question from me to the host, Hydraulic Institute. Are we making this presentation available to participants? Is it going to be circulated?
Absolutely. If that is, I'm going to check with everybody at ASCL to make sure that that is just fine. But yes, we do have a recording of this presentation. I'd be happy to send it to whoever missed a portion of it or just wants to review.
Yeah. There's a question that's just come through about the sealing plans for 2015. Are there any new up-and-coming revisions? The new sealing plans are going to be published in API 682 4th edition. The 4th edition was due to be published last year, but has been held up. The piping plans are in Annex G of API 682. Very usefully, the new API 4th edition has a tutorial note next to the schematic drawing of the piping plan. The various piping plans, there's new piping plans on leakage detection from single seals coming in. There's a new dual seal plan, an unpressurized external source dual seal plan, Plan 55. There's a plan for a dead-ended single seal working in a tapered board seal chamber. That will be Plan 03. And then there's a new plan, which is Plan 99, which is an engineered plan. You can have whatever you want. It's effectively a blank sheet of paper for you to engineer whatever you want, and you can call it Plan 99. Friction of seals, a question about friction of different seal devices and seal types. Yes, there is a difference between different seal types. Non-contacting seals, such as gas lift seals, Plan 74, are virtually frictionless. The seal faces are not in contact whilst dynamic, or shouldn't be in contact whilst dynamic. Conventional wet seals, you have some contact on the seal faces, asperity contact, and you have some viscous drag within the fluid film between the seals. The drag depends on various factors, but the balance ratio of the seal will have an impact on the friction within the seal. The face width will have an impact on the friction absorbed within the seal. Someone's posted a question about a fluoropolymer lined mag drive pump compare with a mechanically sealed metallic pump. I'm probably not an expert to answer on that subject, but I'm sure that information would exist on the Hydraulics Institute website. Generally, to my knowledge, mag drive pumps are, because the coupling isn't direct, there's something like a 10% inefficiency between that and a direct coupled sealed pump. But more accurate information would probably be available on the Hydraulic Institute website or other public domain sites.
So we've got about 2 more minutes before 2. If anybody has any other questions, this would be the time to type them into the Q&A box, lower right-hand corner of your screen. Richard, I don't know if you see any other on your end.
Yeah, there's just one comment. Where would I find info on energy loss due to friction of different types of seals? I don't know as to whether the seal manufacturers would publish frictional energy loss within a seal. There's a formula for calculating the friction of a mechanical seal. It's Annex F. In API 682, there's a formula. There's a breakout torque formula as well, and it asks for you to have knowledge of the spring rate, the balance ratio, and the face width of the seal. And from that, you can work out, by physically measuring the face width of the seal and the spring rate, you can work out the actual friction with any given seal. Obviously, a seal of larger diameter is going to have significantly more frictional loss than a seal of smaller diameter. Question come in about water quality for API plans. River water. What are the quality standards for water? And can API plans be used to enhance water quality at the seals? I'm not aware of flush plans and there being a quality standard for the flush plans. Can the flush plans be used to improve the quality of the water? There are flush plans that include recirculating flush plans that are used where we improve the quality of the flush fluid. That would be such as a Plan 31 cyclone separator. But no, if there's a water quality issue, that would normally be dealt with upstream of the as part of the utilities prior to it getting to the seal flush plan. My own thoughts is that for any seal flush, you want as clean a liquid as you can possibly get. Any dirt or debris is going to have a negative impact on the reliability of the seal.
Okay, Richard, unless you have anything else on your end, I will close up the presentation with a few remarks. Do you see any other questions?
No, I've just had, so my last answer, a recommendation that flush should be ideally filtered to 1 micron. So that's in response to the last question. But I've got nothing else here.
Okay, wonderful. Well, I will just have a few closing remarks and then we'll let everybody get on their way. So we just want to thank everybody for attending this webinar series on Sealing Systems Energy Efficiency, exclusively brought to you by AES Seal. If you have further questions, please feel free to send an email out to our instructor, Mr. Richard Smith, and he can be found at richard.smith@aesseal.co.uk. And I can also email you guys any sort of, or I'll forward the questions on to Mr. Smith as well if that's easier for you. My email address is lsigfrid@pumps.org, and I am the one who had been emailing you the links and everything to begin with, so you probably have that on your email already. Also, you can visit www.aesseals.com for any other information that you might need. AES Seal will also be sending additional webinar information to all of the attendees on the line today. To learn more about mechanical seals for pumps and how to save money through their proper selection, installation, and operation in all types of sealing systems, order the Hydraulic Institute's guidebook on mechanical seals, which can be found at www.pumps.org. So we want to thank you guys for attending this webinar that was sponsored by AES Seals Corporation. We hope that you found it to be extremely useful. Any feedback, I do have a survey going out personally to every attendee tomorrow, so look out for that in your email, and we look forward to feedback. Thank you again, Mr. Smith.
Thank you.
Have a great day.